Hello, and thank you everyone for tuning in to today's webinar, which will be on motor acceleration studies. Let's begin by going over today's agenda. We will begin with an overview of the former Brown Book, which is the new IEEE 3002.7 standard, which is the recommended practice for conducting motor starting studies and analysis of industrial and commercial power systems. We will then cover the motor starting study objectives and analysis, and then we will perform an impact motor starting. We will then go over the data requirements and the unique feature called motor parameter estimation that allows the engineer to estimate motor parameters based on nameplate information. These data requirements and motor parameter estimation are necessary when doing the dynamic motor starting simulation. After going over the dynamic motor starting simulation, we will then do a motor acceleration using transient stability analysis and go over the differences between the three. And then finally, we're going to go over motor starters and motor types, and finally going over the new feature called the motor acceleration result analyzer. So let's begin by doing a brief introduction and background on what the new 3002.7 standard is. For those of you who are familiar with the original Brown Book or the IEEE 399 standard, for motor acceleration, it was in chapter number 9. It was a total of 32 pages. The information, although was relevant at the time, it is now dated, and the ballot was 41 members at the time. So what the 3002.7 did was took the Brown Book, it added new experience, best practices, and also computer modeling to provide us with an updated 3002.7 that is 106 pages long. It includes modern computer-based power system analysis. It provides us with motor starting simulation plus analysis. It was voted by 120 ballot members, and it can be used by both beginner and experienced engineers. So that's essentially our new IEEE recommended practice for conducting motor starting studies in industrial and commercial power systems. Okay, and brief summary on content changes. So we have a table. I've got a table up here with two columns. On the left hand side, it's the Brown Book 399 standard, and then over on the right hand side we have the equivalent 3002.7, but in red we have all of the new sections that are part of the standard. So as you could see, it more than double the amount of information, primarily when it comes to best practices and computer modeling. All right, so why do we need to perform a motor starting studies? Essentially, the main two items is to ensure that the motor will actually start with the voltage drop that is present. And then number two is to ensure that the voltage drop will not disrupt other loads. So this means that the utility bus voltage will remain at greater than 95% of the nominal system voltage, and that the motor control center bus voltage will always remain at above 80%, and any generation bus voltage remains at greater than 93%. Going back to item number 1, ensure that the motor will start with voltage drop. We could see that if the torque load is greater than the available motor torque at slip equals 1, that the motor will not start. So let me quickly introduce what that means. As you could see from following graph, we're looking at a torque versus speed. The bold line is the available motor torque, and the dotted red line is the required load torque. So we can see the difference is our acceleration torque. Nice graph like this, there should be no issues with the motor actually starting. However, if these two were to cross, so if the load torque was actually greater than the motor torque, then we need to look into the motor will not start, number one, and we need to look into either proposing a soft starter or doing other kinds of maybe partially loading the motor as it begins to accelerate. So we're going to go over examples on that. Okay, let's talk about computer-based modeling, because it's a big portion of the 3002.7 standard now. So let's begin by going over these 4 items. So on the top left, we have the static start that we're going to be covering. And this is essentially an impact motor starting. So this is kind of the worst case voltage drop condition. The simulation only requires nameplate information. So it takes, like, for example, the log rotor current, the log rotor power factor, and it gives you a worst case condition. Over on the right hand side, we have a more detailed simulation, which is the dynamic starting, and that takes into account information such as the motor dynamic characteristics. It takes into account the load characteristics requirements, and however, it does not take into account things like generator excitation and governor systems. For that, we look at the bottom left, which is the full dynamics, and that's using the transient stability engine. Now, on the bottom right, we have characteristic curve. It's a way for the engineer to enter the motor characteristic curves as provided by the motor manufacturer. So let's begin by illustrating a simple voltage drop. We'll call it an impact start. On the left hand side is our time equals 0 seconds. This is a system that is in steady state. If you notice on the bottom, the loads on the left hand side are running and the system is on steady state. So we can see the voltage drop at the generator bus and at the various medium voltage and low voltage locations. Now, on the right hand side, what we do is we start that large 1000 horsepower motor. It's all the way on the bottom right. So we can see the impact at t equals 1 second of what happens to the voltage drop now at your generation bus, as well as the distribution and the low voltage bus over on the left. So this is essentially what an impact motor starting is, and I will cover that here in just a second. But before, I'd like to go over the static versus dynamics in a more graphical form. And over on the left hand side, you could see how whenever we start a motor, doing a static or an impact motor starting, how we see the graphs as piecewise function, which means that we get a worst case simulation on what's going on with the voltage and the current. However, it doesn't tell us the full picture. It doesn't tell us how long the motor will take to start, and it most importantly, it doesn't tell us whether the motor starts or not. As opposed to the dynamic motor acceleration on the right hand side, you could see the output graphs have a lot more definition because it's an iteration over time, so we can see what's going on with the power, current, voltage as that motor is starting. It will let us know how long that motor takes to start, and more importantly, whether that motor starts or not. The dynamic motor acceleration simulation will give us far more characteristics, and obviously it does require more information, more input information, which is information that we will cover. Okay, Now let's talk about the objective and methodology. So essentially, split into two. We have the design phase where we look at voltage dip analysis, and then we have under operation and expansion phase. For the design phase, we would be modeling typical starting motor, minimum, normal, and worst case loading, simultaneously starting motors at the same time, source contingency, so single-ended feed versus parallel, and also using that information for cable sizing. However, for operation and expansion phase, we would be using the scenarios to identify existing starting issues, for plant operating configurations, for setting protected device settings, as well as investigating any type of nuisance trip on protected devices. Let's go over data requirements for performing motor acceleration. You have your typical impedance information that you require for load flow and short circuit analysis. All of that information is to be present, but additionally we need information such as the load characteristics and motor characteristics. So let's go over these data requirements. All right, so let's begin first by going over the differences between a static versus dynamic simulation. So we already know what a static or an impact motor starting is, and I'm going to show everyone where to run it from. So we run it from make sure that we go into motor acceleration, and under motor acceleration we have on the right hand side toolbar the static motor starting, which is the second one, and then on top we have the dynamic motor starting. Obviously the dynamic motor starting will require more information, but the static motor starting has a place where if you only have the nameplate characteristics of the motor and you need a quick impact motor starting with the worst case condition, you're not concerned whether the motor will start or not, then this simulation can be used. However, once you get into detailed engineering, you need to figure out how long that motor will take to start. You need to compare between impact on various soft starters, whether the motor will start or not, then the dynamic characteristic would be required. So let's go over some of the data requirements by opening the motor editor page. So for both simulations, static and dynamic, the nameplate of the motor is essential. So you want to make sure that the horsepower is entered, the power factor, the efficiency, number of poles. So this is information that you would find typically on the nameplate of the motor. Heading over to the next tab is making sure the subtransient reactance is entered, or if you don't have the subtransient reactance, you want to make sure that the log rotor current is entered. Then ETAP will back calculate that information for you. So this is the minimum required information for doing not just static or an impact motor starting, but also for doing a short circuit analysis or doing an arc flash. So no other data requirements really are necessary for that. However, when you're getting into the more detailed dynamic motor acceleration, then we need to go over to the next tab, which is the model tab, and you have the ability to enter the motor dynamic characteristics in 3 different ways. The first one is by using the circuit equivalent model. So this is essentially some of the manufacturers in the past for older motors will provide you with the equivalent circuit. As you could see here in red, they would give you the impedance and time constants for the type of motor that you had. more and more that's becoming less available. And typically what the manufacturer will now provide you is the curves. So what you're seeing on the right hand side. So essentially what we're looking at is starting from the top, you have the torque versus the slip, or in your case you probably get from the manufacturer the torque versus the speed. Below in green you have the current versus the speed, and then below you have the power factor of the motor versus speed. So this is essentially what the torque and current characteristics of and power factor of your machine are as it begins to accelerate. ETAP provides you the ability to enter this information into the library. The motor manufacturer will typically provide you with this data in either Excel or printout format, and you can quickly go and enter it into the library and select it from the library. Now, for those of you who are at the front-end engineering design of a project or the feed, a lot of these curves are not available, but you need a dynamic starting, right? We have a motor parameter estimation and tuning tool that is right here. And this utility actually allows you to select the input data straight from the nameplate, and it automatically will estimate the dynamic characteristics for you and populate this information, the characteristic model for you. So parameter estimation and tuning is essential for those of you who maybe are at the feed stage, do not have all of the dynamic characteristics, right? But you need to get going with a dynamic simulation for setting your protected devices or other detailed engineering. Or maybe you have a very old facility where you need to do a motor starting for a medium voltage motor, but not all the dynamic information for the motor is there. Maybe the manufacturer went out of business. Maybe the owner operator of the facility did not keep good records of the machines, the motors. So that information is not there. So that's where parameter estimation tool would be essential for you to just enter the nameplate information and then allow ETAP to provide you with, use that data to provide you with dynamic characteristics so you can get going with a more detailed simulation of your motor acceleration. Continuing with the information required for a dynamic motor starting is the inertia must be entered, and also the load information needs to be entered. So there is a library full of typical loads within ETAP, but some of you have this information. The load characteristics, it would be the black line that we see here that sits just below the motor torque. As you could see, there is enough clearance between the two where this motor should actually be able to accelerate this load and get it started. However, if that's not the case, if these two lines are crossing, there's a good possibility that motor will not start across the line. So you need to look at other solutions such as a soft start or a perhaps partially loading of that motor as it begins to accelerate. So now that we have the additional information that's required for dynamic simulation covered, what I like to do is now I like to perform or run a dynamic motor starting. So before I run a dynamic motor starting, what I like to do is open the study case and show everyone what we're doing. So we're essentially, we have 3 events. So this is essentially starting several loads over a period of time. So at 100 milliseconds, what we're doing is we're starting the synchronous pump that you see over on the left hand side, which is 1250 horsepower, connected to a medium voltage bus, and also a pump 1 that is connected to a 4 kV bus or 4160. Then at 800 milliseconds, we're going to bring in a large load online. And then at 4 seconds, we're going to start a 200 horsepower motor. And we want to see, we essentially want to see what the impact on the system this simulation is going to have. So let's go ahead and run a dynamic motor starting. So I click on the top right, dynamic motor starting. We see the simulation run. We have a motor starting time slider where the user can, for example, scroll over time. So you could see here at 100 milliseconds, the synchronous motor on the far left begins to accelerate. And then the other motors, which happen to be inside some of these composite networks, are also starting. So to get a better feeling for the results, let's go ahead and look at what's happening at some of these critical locations. Let's take a look now at what's at the loads. So back to the motor starting plots. Now we're gonna be looking at the 3 loads that we started, and we're gonna take a look at the speed and also the current for these 3 loads. So what we have here on the left hand side is the speed versus time. So for the large synchronous motor in blue, we could see how long it takes this motor to reach synchronous speed, all 3 of them actually. And then over on the right hand side, we could see the current being drawn by each one of the machines. We can see the events here. So we could see the first event at 100 milliseconds, the second event here at 800 milliseconds, and then the third event here at 4 seconds. Okay, now that we had a chance to go over the static and dynamic motor starting, let's run now this simulation using the transient stability. Where the main difference will be the amount of information, the vast amount of information that you can get. So for example, for a given bus, right, using motor acceleration, we're only able to see really the voltage drop. We can't see, what the frequency is doing, and the reason for that is because we're not taking into account our generator or synchronous machine exciter and governors. For that, we need to perform this simulation using transient stability. So we head over to the transient stability analysis, and we're going to perform the exact same simulation using transient stability. However, we're gonna bring in the generator, the synchronous generator, online. So to do that, I'd like to introduce the configuration manager. The configuration manager is the utility that allows you to model different operating conditions, not only for motor starting, but also for arc flash analysis and multiple other simulations like short circuit analysis, where there's a strict requirement to model more than one scenario. So in this case, I will zoom into the generator section. Under normal operating condition, you will notice that the generator breaker is set to open. However, if we select emergency, now that synchronous generator breaker is closed. So again, you can quickly toggle between the 2 operating conditions, normal and emergency. So in this case, we're going to go ahead and perform a motor starting using transient stability simulation. We're going to go from motor acceleration to transient stability analysis. And the simulation that we're going to perform is we're actually going to bring this motor here online at 100 milliseconds. And then at 4 seconds, we're going to bring in this induction motor online. So it's essentially a sequence of events. To perform this sequence of events, we open the study case for transient stability, and we could see here that we have at 100 milliseconds starting of the synchronous motor, and at 4 seconds we bring in the induction motor number 2. The reason why I began the simulation at 100 milliseconds is because we want to see what the system is doing under steady state before we apply the disturbance. In this case, starting of synchronous motor. So we're going to click OK here, and I will begin by running this transient stability. And the first thing that we see is my system under steady state. This is at t equals 0, as you could see here from the time slider. And we could see what the system frequency is at the different locations. So at 60 Hertz here, 60 Hertz right here. Again, this is taking a snapshot of the system before we actually start the first motor. So let's skip to the first action. So at 100 milliseconds, we begin by starting of the synchronous motor. And as I begin to scroll to the right, you could see how the snapshot automatically is updated. If I go into the next action, which is at 4 seconds, we bring motor 2 online. And although it's great to see, you know, the snapshot play in the one-line diagram, the vast majority of information is going to be on the plot manager. So let's begin by taking a look at what's going on with the frequency at these two locations, these two bus 2A and 2B. So I'm going to open the plot manager. I will head over to bus number 2A, 2B, and I'm going to look at two things, frequency and also voltage drop. And on the left-hand side, we can see the frequency at these two locations. We have these two events, so 100 milliseconds, and then over here, 4 seconds. So you could see how the frequency at these locations begins to stabilize after we start the motors. Granted, this is less than 1% change in frequency, so it's not enough to activate any of our frequency relays. Now over on the right hand side, we could see now the voltage drop as we be at 100 milliseconds, and also when we start at 4 seconds when we start the second motor. And we could see how for starting the first motor at sub 2A, the voltage drop is about 6%. And on the other bus, it is when we at 4 seconds when we started the induction motor is about 4%. So it's very useful to be able to visualize this much information and at the same time apply the events on the plot. Next, what I would like to go over is the motor starting devices. And to do that, I would like to open this composite network where I actually have a motor fed by a VFD drive. Now, as part of the three-dimensional database, you have, yes, we looked at the configuration manager, but there's also the revision manager where the engineer can model different starters. In this case, we have this project that has 4 different starters. We have an auto transformer, capacitor starter, no starter, so across the line, and VFD starter. So as we toggle, we can also see the one-line diagram refresh. So we're looking at VFD starter. If we go to no starter, you could see the bypass across the VFD drive. And like that, we can toggle to auto transformer or capacitor starter. One way to automate or run multiple of these simulations is by running the scenario wizard. So on our scenario wizard is essentially a way to automate running multiple scenarios or what if conditions. In this case, what we're looking at is essentially the user, you can specify which configuration, whether it's normal or emergency, the type of study to be done. So in this case, we're doing a motor starting. And then you can specify also the study case options and the output report. So having multiple of this, we can quickly automate and run as batch and quickly compare between the different motor starters. Now that we understand and know how to perform multiple scenarios using multiple starters or using a variety of different operating configurations, the ability to now analyze and compare between the various scenarios and starter types in a report analyzer format becomes extremely important. So starting with ETAP 20, the motor starting analyzer can be generated using scenarios. And what we're looking at on the screen is essentially an output report of such report analyzer. So each one of these rows represents a different starter type. So we have a total of 5 different starter types, and this is where we can quickly compare which type of starter is better suited for the application. Now moving on to illustrating an example with and without starter, in this case a VFD drive. The plot view allows the user to quickly display various characteristics such as motor speed, bus voltage, motor current, with and without starters by running these scenarios and plotting them on the same graph. So what you're looking at on the screen is, in orange you have starting of a motor without a VFD drive, as compared with the blue line, which is starting of the motor with a VFD drive. And you could quickly see the comparison between motor speed, which one took faster to start, what was the impact on the bus voltage, what was the impact on the line current, and on the center is essentially the VFD drive controller that was used for this simulation. And supported in ETAP is the partial winding start, the white delta start, the capacitor start. So in dark, solid line is the terminal current in percent of full load amps versus the motor torque in the dotted line. And you could see the comparison between the different starters. As I mentioned earlier, the motor starter is selected from the motor starting page and can be set by the user from here. In conclusion, ETAP offers the engineer the ability to perform motor acceleration at the design phase as well as during operations and during the life of the project. Under design phase, the engineer can perform static motor starting, model minimum, normal, and worst case loading conditions, and do cable sizing based on voltage drop. Under operations and throughout the life of the facility, engineers have the flexibility to model different operating scenarios to identify existing starting issues, to model planned operating configurations, and also to study various motor starters and the impact they have using the result analyzer and the protection evaluation tool. Thank you for attending today's presentation on motor acceleration.